Thank you for the introduction. My name is Benedikt. I'm a cryptography researcher at the Ethereum Foundation, and this talk is going to be about quantum resilient Ethereum. So let me set the stage and tell you what I'm going to be talking about. So at this conference, we talk a lot about decentralized finance, and as you know, decentralized finance builds on blockchains. One of the most important blockchains for the DeFi space, if not the most important blockchain, is Ethereum. And Ethereum, as other blockchains as well, builds on a beautiful science called cryptography. So cryptography is the science that brought us encryption and digital signatures and all of that cool stuff. And you can summarize it as the science of secrets. Now, the story of this talk is that cryptography is threatened by quantum computers. So this guy here is Peter Shor. He developed a quantum algorithm that breaks most of the cryptography that we use nowadays on the internet and also in Ethereum. So let me make this a bit more explicit. So as I said, we have DeFi applications, they build on Ethereum, and Ethereum itself builds on cryptography. Now, as I have said, if you have a large-scale quantum computer, which luckily doesn't exist yet, you can break most of the cryptographic systems that we use nowadays. And I should mention, just to complete the picture, that this is not unique to DeFi or Ethereum. This also covers classical finance, or in general our modern communication that depends on cryptography. So luckily, cryptographers were not lazy, we were not sleeping, and we have been aware of this problem for a long time. So this is where the field of post-quantum cryptography emerged. So these are cryptographic constructions that are secure even against a quantum attacker. And the foundations of those go back to the 70s and early 2000s. And so far, we even have NIST standards that standardize encryption schemes and digital signature schemes that are secure against quantum computers. Now, the strategy of the Ethereum Foundation to make Ethereum resilient against quantum computing is to rely as much as possible on these standards just to ensure compatibility and interoperability, but also to use some custom solutions because we have quite unique challenges in the Ethereum space. Now, a natural question to ask is, when would this happen? When would quantum computers be there and attack our cryptographic systems? And to be honest, I cannot give you an answer to that. I can just give you like 3 example timelines. So in the first timeline, we would expect a large-scale quantum computer to materialize somewhere in the early 2030s. And actually, if you talk to experts and like quantum engineers, they think this is a very likely timeline. Okay, so the second and third scenario is that it takes much longer or quantum computers never arrive. And actually, there are experts out there that are quantum skeptic and that think there is some fundamental barrier. But I think the risk of hoping for scenario C here is just too high. And this is why there's a sort of broad consensus in the Ethereum community and also Ethereum Foundation that we want to make Ethereum quantum ready by, say, 2028. Okay? And sort of the key takeaways from this talk are that 1, there is this quantum threat, and 2, we are prepared, we have a plan, and we know what we want to do to make Ethereum quantum resilient. Okay, so let me tell you a bit more now in detail about Ethereum and what kind of cryptography we do at the Ethereum Foundation. So, as I've said, we have all these applications, they build on Ethereum. And if you ask me to summarize what Ethereum is as a sort of a service that it provides to these applications, then I would say it's a decentralized system that allows us to agree on state and update that state according to some programmable rules. So this sounds quite abstract. Let me make this more concrete by giving you 2 examples. So the first example is the example of simple money transfer, simple payment, if you just use it as a currency. Here the state is the balance of users, the updates are financial transactions, so Alice sends to Bob, and the rules would be something like, I can only spend what I have already received before, so I cannot create money. Now, a bit more sophisticated would be a loan. Here the state would be how much balance is still owed, and an update would be a repay, and the rules could be something like, if I miss a repay deadline, then we add some penalty. Okay, so all of these kinds of applications can live in parallel on the Ethereum chain. And to do that, Ethereum uses cryptography. Now, because cryptography is so important for Ethereum, we have our own cryptography research team at the Ethereum Foundation. This team right now has 6 full-time researchers. We all have sort of academic backgrounds and also like blockchain backgrounds, very diverse backgrounds, but what we do is we bridge the cryptographic research community and the Ethereum community. And the goal of this is to make sure that every update that we do in Ethereum builds on strong cryptographic foundations, and everything that we do is secure from a cryptographic standpoint. And of course, this also includes doing research on post-quantum cryptography and figuring out how we make Ethereum secure against quantum computers. Now, because this threat is coming closer and closer, the Ethereum Foundation recently has started a new dedicated team, the post-quantum team, which is now growing. And the goal of this team is really to take theoretical ideas, research ideas, and all of these innovations and push them towards production. Okay, and of course we cannot do this all by ourselves. We also collaborate a lot with academics, with researchers from the Ethereum community, and we organize workshops. This picture is from a very nice workshop that we had in Cambridge with over 50 people there that was just dedicated to post-quantum Ethereum. Okay, now if we want to understand what quantum does to Ethereum and how we update it, we need to understand what kind of cryptography are we using in Ethereum. Okay, I've already mentioned encryption and signatures. So for Ethereum and generally for blockchains, signatures are more important. And you know, there's no cryptography talk without Alice and Bob. So here are Alice and Bob. And Alice sends a message to Bob saying, I sent 5 ETH to Bob. Now, how can Bob be sure that Alice has really sent this message and no one has modified that message? And the solution is digital signatures. So here Alice would generate a secret key and a public key. She would keep the secret key to herself and reveal the public key to everyone else. And now when she sends a message, she would sign it using the secret key. Now Bob, when he receives this message, he would take the public key and verify it, and he can be sure that really Alice has sent it because you can only sign if you have the secret key. Right? This is the central security guarantee that digital signatures give us. Now, how do we use this in Ethereum? Here's a simple example. Whenever you post a transaction on chain, for example, Alice spending coins to Bob, then Alice would sign this message so that everyone sees that really it's Alice that sends this transaction and no one else can just spend Alice's coins. Now, let's think back about quantum attackers. So a quantum attacker, as I said, can break cryptography, so it can break the guarantees of this scheme. In particular, a quantum attacker can forge signatures, so it can send messages on Alice's behalf. And that's very bad, right? Because now the quantum attacker could post a transaction on chain that spends all of Alice's coins. Now, luckily, this only holds for some parts of cryptography, for what I would call classical schemes. But as I've said, there's this whole area of post-quantum cryptography, and there are post-quantum signature schemes. So classically, what these signature schemes use is they use hard mathematical problems, such as integer factoring. I give you p times q, and you have to find p. And if these problems are hard, then the schemes are secure. And this is true also for the schemes that are used in Ethereum. Now, as I've said before, there's this Shor's algorithm from 1994 that breaks these kinds of schemes. So Shor's algorithm can efficiently factor an integer into its prime factors. Now, post-quantum schemes rely on a different sort of problems. For example, finding short vectors in lattices or hash functions. And NIST has standardized encryption schemes and signature schemes that rely on lattices or hash functions. Now, for Ethereum, our current thinking is that we will most likely just rely on hash-based schemes because they are very well studied, they have a very solid security foundation, and they give us some unique features. Okay, now let me tell you how we take these new schemes and how we integrate them into Ethereum. And to understand that, we first need to understand some basics about the structure of the Ethereum protocol. So the Ethereum protocol is split into 2 layers, the execution layer and the consensus layer. So as I have said before, the job of the Ethereum protocol is to allow us to agree on state, update that state according to some programmable rules. Now, what are these 2 layers doing? The execution layer ensures that every state update is authentic and correct. So for example, if Alice sends money to Bob, then the execution layer would verify that this transaction comes from Alice by verifying a digital signature. And it would check that Alice only spends the coins that she owns. Now, a quantum attacker could break this, as I've said, by forging signatures, so it could send transactions on Alice's behalf, and in that way, the quantum attacker could just steal Alice's coins. This is, of course, very bad. Now, the consensus layer ensures that we all agree on a certain state, so that without a centralized service, we all are in agreement what the state of the world is. And to do that, Ethereum uses a protocol called proof of stake that is based on voting. So you vote for blocks using digital signatures again. Now, the consequence of a quantum attacker here would be that the attacker again can forge signatures, and this would allow the attacker to split the network. So say half of the world would think this is the state of the world, whereas the other half of the network would think this is the state of the world. And this is of course bad. It breaks all of our guarantees, and we can no longer work with such a system. So the conclusion is that we need solutions for signature schemes for both of these layers, and they both have slightly different requirements. So let me talk about the execution layer first. So again, this is about how to verify that transactions are authentic and correct. So let's look at a classical transaction that is sent right now from a legacy account. So if I want to look at this transaction and check whether it's valid, I need to do two things. First of all, I need to check that the signature is valid. This ensures that the sender is really who he claims to be. And second, I need to check that the logic follows the programmable rules that I've mentioned. And this is covered by a smart contract. So this is a piece of code that lives on chain and that defines these rules. Now, if I have a quantum attacker, the quantum attacker can only attack the first part. So it can break signatures. Now, one way to deal with this, and this has come up in the Ethereum context, is called account abstraction. So the idea is we already have these smart contracts, which are very flexible. So they define programmable rules. Why not use them also for signature verification? So the idea would be if you set up an account, you would specify via a smart contract what the signature verification algorithm would be. And this can now be a post-quantum signature verification algorithm. And then whenever the transaction is verified, the verifier would look at this smart contract. And in this way, you can easily set up an account that uses a post-quantum signature scheme. Now, I should say that we already have this in Ethereum. So right now, you can already do these kinds of accounts. You can use account abstraction and actually run post-quantum secure accounts. So you could already switch. And soon we will have an update that actually makes this way cheaper than it is right now. And I think the main tool that enables this are smart contracts. So I guess chains without smart contracts have a much harder time of updating. Now, let me tell you a bit about the consensus layer. So remember, this is the layer where that ensures that we all agree on what the state is, and we do that by this sort of voting protocol that uses digital signatures to vote. So here, what we use right now is called BLS signatures. It's a specific signature scheme that has some very unique feature, and that is that you can take a long list of signatures, and you can compress them or aggregate them into one short signature that represents the whole list. And this is very useful if you want to save bandwidth on the networking layer. Unfortunately, this is broken by a quantum computer, and so far there has been no quantum analog that has a similar feature until in early 2025, we published a paper that actually gives us a hash-based and therefore post-quantum version of such a scheme. So it again allows you to aggregate a long list of signatures or votes in this case into a short aggregate signature. And this will now serve as a drop-in replacement for BLS signatures. Okay, so what we have done is we wrote this paper and we wrote even more papers, but we didn't stop at the theory side of it. So actually there are now cryptographic libraries that are open source and that implement these new cryptographic schemes, and there are sort of engineering efforts and devnets, meaning small clones of the Ethereum protocol that already use this kind of cryptography and that run. And there are weekly meetings where developers coordinate on these devnets, and we run tests to make sure that really these schemes behave as we expect. And of course, we are still open to sort of new ideas, and we sponsor researchers that try to improve the efficiency of all of this via grants, and we host the workshops that I've mentioned before. Okay, so all of this may sound like a very ambitious goal to you. I mean, after all, there is this very important protocol that secures billions of dollars, and while it is running, we want to sort of change the basis of all of it. But I'm pretty confident that we can make it, and I give you 3 reasons why this is the case. So the first is dedication. So the Ethereum Foundation has spent and will spend a lot of money on this topic, and we have a lot of manpower on this topic. The second argument is that everything we do is based on solid research. It's not just made up in 5 minutes. Actually, the techniques that we use, they are not fundamentally new. They date back to the 70s, where Merkle trees and hash-based signatures have been studied. And via recent breakthroughs, we just make them more efficient and give them more flexibility. And the third thing that I want to mention, and this has been mentioned on the panel before, is that the Ethereum community is very experienced with doing these sort of updates while the chain is running. So one example is the merge, where we switched from proof of work to proof of stake. And since then, there have been regular Ethereum updates once or twice a year while the chain was running. So I'm pretty confident that the Ethereum community can deal with this major update as well. And yeah, that's all I want to say. Thank you for your attention.
Thank you, Benedikt. Maybe I might chime in with one important question. I think that's very, very, very important. So one thing is that you update Ethereum. How important is it that the users play that game? Because I think when you look at some Bitcoin wallets, they lie around for 12 years. They didn't move anything.
Yes.
So do the users afterwards have to do something to be safe?
Yes. So I actually had a slide. I removed it. So if you look at this, like these new accounts, then of course you as a user need to create a new account that has this feature, and you need to move your funds there. But there are actually solutions for accounts that sleep, and even after a quantum computer arrives, as long as they have never signed any transaction, we can still save them. So there are ideas in the Ethereum community to do that, and I think this is very nice. If, on the other hand, you have used your account, then I think you're doomed.
Okay, so that will be a very interesting phase after the important
Yes.
upgrade. Okay. Any other questions? We have 1 more minute.
You said 10 to 20 million dedication to protect the chain against these threats. Could you elaborate on roughly how much percent it is of what the foundation earns, or because 260 billion, I think I just researched, is the current market value of Ethereum.
Right.
Euro.
Okay, so the Ethereum Foundation doesn't
short.
have
It sounds not much to me. That's what I'm trying to say.
Oh, I see. Well, it sounds a lot to me, so that's all I can say.
Any other questions? Otherwise, we go for the next topic. Thank you, Benedikt. There's another question.
Is there a need for sidechains or layer 2 solutions to also upgrade?
Yes. I mean, they also use cryptography. They also use sometimes even more complex cryptography, which is maybe harder to update. This was just about Ethereum layer 1. Other like layer 2s, they need to update as well. Yes.
Oh, now the questions come in. This is the last one.
Thank you. Your new solutions, quantum secure solutions, is it for the time after the switch, or what is with the data before your solution, post-quantum secure solutions?
Yeah, good question. So there are these 2 layers, right? There's the execution layer and the consensus layer. So the execution layer, we need to switch that before a quantum computer arrives, right? And then everyone will use this new kind of cryptography. For the execution layer, it's about users' accounts. So actually you have to tell the user, please switch as soon as possible, and then some users will switch and others will maybe not switch, and this goes back to this question. If a user didn't switch when there's a quantum computer, but that user never spent anything, never signed a transaction, then actually that user can still be rescued. If the user already signed a transaction and there's really a powerful enough quantum computer, then it's kind of a bad situation.